Welcome to Systematic Physics. Here we will be guiding you for content of physics for boards, NEET and JEE. Rotational motion, competitive exam corner, level 2. These are problems little higher than what you have studied in level 1. Let us start. What are they saying? A mass M supported by massless string wound around a uniform hollow cylinder of mass small m and radius capital R. If the string does not slip on the cylinder, with what acceleration will the mass fall on release? The options are given to you. Observe this diagram very carefully. Now there are two bodies. One is cylinder, other is small mass m, which is moving down. We have to apply FBD. FBD means free body diagram for small mass, also for the cylinder. I'll consider small mass first. Now if you see the diagram, mg is vertically downwards, always. Tension is along the string and away from the body. So here it would act away from small body in the upward direction, and same in case of cylinder. At that end it will act downwards. So again mg is downwards, tension T is upwards. Now in this case acceleration is downwards, so its inertial force ma would be in the upward direction. So if I apply the D'Alembert's principle, I get mg minus T is equal to ma. Now we know that A is equal to R alpha. I substitute that value back in the previous expression. So what I get? mg minus T is equal to mr into alpha. Come back to the cylinder. Now what is a torque produced on the cylinder? Torque produced on the cylinder is a force acting on the cylinder and perpendicular distance between line of action of force and the point of rotation. So T into R is your torque produced. Now torque produced, there is one more formula, that is I into alpha. It is a hollow cylinder, so I would be equal to mr square. So I get T into R is equal to mr square alpha. Now I'll solve this equation number 1 and 2 simultaneously. I'll get A is equal to g by 2. Hence the acceleration of the mass falling down is what? G by 2. So option B is the correct answer. Now a pulley of radius R is rotated about its axis by a force F is equal to 20T minus 5T square Newton, where T is measured in seconds applied tangentially. If the moment of inertia of the pulley about its axis of rotation is 10 kg meter square, then the number of rotations made by the pulley before its direction of motion is reverse is. Options are there in front of you. Now you know that F is equal to 20T minus 5T square. Now I into alpha is torque. F into radius of the pulley is also a torque. So I into alpha is equal to F into R. Alpha is equal to F into R upon I. You can see that in the expression. F is known to you, 20T minus 5T square into 2 upon 10. I simplify that expression. So alpha is equal to 4T minus T square. Now what is alpha? D omega by dt. So I get d omega by dt is equal to 4t minus t square. Now here I'll have to integrate the expression to get the value of omega. So that omega would change from 0 to omega and time would change from 0 to small t. When I integrate above expression, we get omega is equal to 2t square minus t cube by 3. Now when the direction is reversed, any body which is moving in a particular direction, for it to reverse its direction, at one point its velocity has to be 0. So omega has to be equal to 0. So if I do that, I get two roots for the above equation. That is t is equal to 0 or t is equal to what? 6 seconds. So now d theta is equal to omega into dt. Omega is known to you, 2t square minus t cube by 3. If I integrate this expression from 0 to 6, I will get the angle turned by the pulley, and that angle turned theta is equal to 36 radians. So number of revolutions is always angle turned upon 2 pi. Angle turned is 36. 2 into pi, it's obviously less than 6, right? So what's the option? Option is A. A thin uniform rod of length small l and mass small m is swinging freely about a horizontal axis passing through its end. Its maximum angular speed is omega. Its center of mass rises to a maximum height of. Now understand one thing. its kinetic energy of rotation would be converted into potential energy. So we need to equate those two energies. That is half I omega square, that is equal to mgh. It's a rod rotating about one of its end. So its moment of inertia is 1 by 3 ml square. When I cancel out the terms, I get h is equal to 1 by 6 L square omega square upon g. So that is option D. For the given uniform square lamina ABCD, whose center is O, I have to find out what is the correct expression. Let the each side of square lamina be D. You can see that in the diagram. We know IEF is equal to IGH and IAC is equal to IBD. These are two axes perpendicular to each other and in the plane of the lamina. Now I know IAC plus IBD is equal to IO, perpendicular axis theorem. So 2IAC, because IAC is equal to IBD. So 2IAC is equal to IO. I also know IEF plus IGH is equal to IO, perpendicular axis theorem again. So I get 2IEF is equal to IO. So from these two expressions, I get IAC is equal to IEF. Remember one thing very clearly. If you have any axis in the plane of the lamina, the moment of inertias about those axes would be same. So what I get, IAC is equal to IEF. Now IAD is equal to IEF. Understand what is IAD? About one of the sides is equal to IEF plus m into d by 2 the whole square. That is distance between AD and EF is equal to d by 2. So d by 2 the whole square. So when I open the bracket, what I get? md square upon 12 plus md square upon 4. So that is IAD is equal to md square upon 3. So that is equal to 4 times of IEF. I hope you understood. This is problem number 5. A circular disc of radius r is removed from a bigger circular disc of radius 2r such that the circumference of the disc coincides. The center of mass of the new disc is alpha into r from the center of the bigger disc. The value of alpha is, the options are given in front of you. Let us find out the mass of the disc which is removed. What is the mass per unit area of a whole of a disc? That is total mass upon area of full disc. That is pi into 2r the whole square into the area which we removed, that is pi r square. So that is m by 4. Now what would be the mass of the remaining disc? Capital M minus m by 4, that is 3m by 4. Now we have two bodies. One body is the remaining circle and one body is the circle which is being removed. Now the distance between the center of new shape and the center of mass is alpha into r. I will take moment about that particular point. So that moment would be 3m upon 4 into alpha r plus m by 4 into r, that is equal to 0. If you observe, one of the moment I had taken negative. Reason, because these are two different bodies on two different sides of center of mass. So they will produce, if one produces clockwise, other has to produce anti-clockwise moment. So one sign has to be negative. If I solve the above expression, I get alpha is equal to 1 by 3. That is option A, which is the correct option. Now problem number 6. A round uniform body of radius capital R, mass capital M and moment of inertia I rolls down without slipping. An inclined plane making an angle theta with the horizontal, then its acceleration is. If you observe this expression, you would realize that we have derived this in the discussion of the theories. Now when the body rolls down, its total energy is mgh. That gets converted into kinetic energy of rotation plus kinetic energy of translational motion. So mgh is equal to half I omega square plus half mv square, where v is equal to r omega. So omega would be v by r. I substitute that value. So when I equate all this, I get v square is equal to 2 mgh upon m plus I by r square. I cancel m from the numerator and also from the denominator. I get an expression for v square. Now that h should be replaced. You know that sine theta is equal to opposite upon hypotenuse. So h by s is equal to sine theta. So h is equal to s sine theta. I substitute that in the equation. I get A is equal to G sine theta upon 1 plus I by mr square. This is the expression which we had actually derived in the theories. Problem number 7. A force of minus Fk cap acts on O, the origin of the coordinate system. The torque about point this is what? Tau is equal to R bar cross F bar. Your F bar is known to you, F into K cap. So when you multiply this, you take a cross product of these two. You get tau is equal to F bracket I cap plus J cap. Problem number 8. A thin circular ring of mass small m and radius capital R is rotating about its axis with a constant angular velocity omega. Two objects, each of mass capital M, are attached gently to the opposite ends of a diameter of the ring. The ring now rotates with an angular velocity of omega dash, which is equal to, the four options are given in front of you. There is no external torque acting, so we can use law of conservation of angular momentum directly. That is, I1 omega 1 is equal to I2 omega 2. Omega 1 is omega, omega 2 is omega dash. Now since it is a ring, its moment of inertia would be mr square. And since the masses are attached, that moment of inertia would be added in the next part. That is, I2 would be equal to mr square, which is moment of inertia of a ring, plus 2mr square, which is moment of inertia of this additional two masses. So omega dash is equal to m upon small m plus 2 into capital M into omega, which is expression D. Problem number 9. Observe this problem carefully. This was asked in one of the JEE papers long back. Understand, a T-shaped object with the dimensions shown in the figure is lying on a smooth floor. A force F is applied at a point P parallel to AB, such that the object has only translational motion without rotation. Find the location of P with respect to C. Options are given in front of you. For pure translatory motion, net torque about a center of mass should be equal to 0. Thus, F is applied at a center of mass of the system. I consider the origin at point O as shown in the diagram. The coordinates of that point would be 0, 0. The coordinate of the vertical line, which you can see, since its length is 2L, its center of mass will have a coordinate 0 and L. So I know formula that OP is equal to m1y1 plus m2y2 upon m1 plus m2. m1 is m, y1 is 0, m2 is equal to twice of m because the second part has double the length, and its center of mass y2 is at L. So if I substitute that, I get OP is equal to 2L by 3. Now I need to find out that distance from point C. Total length is 2L. OP is equal to 2L by 3. I subtract 2L minus 2L by 3. I get 4L by 3. Problem number 10. Initial angular velocity of a circular disk of mass capital M is omega 1. Then two small spheres of mass small m are attached to two diametrically opposite points on the edge of a disk. What is the final angular velocity of the disk? There is no external torque acting. So I can apply law of conservation of angular momentum. So that is half mr square into omega 1 is equal to half mr square plus the moment of inertia of two other masses, that is 2m into r square. So I get omega 2 is equal to bracket m upon m plus 4 into small m into omega 1. So the option becomes C. That is end of level 2.
Please like and share the video with your friends and subscribe to stay connected with systematic physics. Thank you.